We're Zoom people. Okay, so I'm going to be talking about just a kind of a whirlwind of different projects that span boreal and urban environments, but the through thread is methodological. So with an emphasis on high resolution, be that spatial resolution, spectral resolution, and or temporal resolution, trying to get the highest of all the resolutions together, and some of the platforms as well. So drones and CubeSats and airborne LiDAR and hyperspectral data. So let's see, advance, there we go. So basically, we'll divide up into a geographic region here and talk about a couple projects that I've been working on through the NASA Carbon Monitoring System funding and collaboration in interior Alaska. So forest structure mapping, species, above ground biomass, that kind of stuff, and shrub biomass mapping with UAV and piloted aircraft. And then move completely across the country from Alaska back to the mid-Atlantic and talk about high resolution urban forest monitoring with a little bit of DC, a little bit of Baltimore, and a little bit of Philadelphia. And then have some time for some discussion, hopefully. So the first project is my first UAV project in Alaska. And so this is a collaboration between mostly Forest Service and NASA. And the idea is, like, Forest Service would like to figure out how to better measure at high resolution some key forest attributes like above ground biomass, basal area, and tree density. And a key add-on to that is they also want to be able to allocate those quantities by species. So Alaska, interior in particular, presents difficulties. It's hard to get field crews out into all of these areas. It's extremely expensive, and it presents some opportunities for cost saving through this collaboration, particularly using LiDAR data from the Goddard LiDAR hyperspectral thermal platform, but trying to get more information from UAV data also. So that's this first project here. So let me introduce you to the drones that I'll be talking about through this presentation. On the left, you've got Agnes. Agnes is the workhorse, just the standard Best Buy DJI Phantom 4 Pro that basically has, a GoPro style high-res 20 megapixel RGB camera on it. And on the right, you've got Mo, who's a DJI also, but a Matrice 210, so a little more on the industrial scale, can fly two cameras simultaneously. You're on the far right, you're seeing the Red Edge camera, so that's 5-band multispectral camera that I won't really be talking about too much today. And then Mo currently is outfitted with the ZenMuse XTR, so it's a radiometric thermal camera that's going to come into play in some upcoming work with UMBC. So one main challenge of going to the industrial model is trying to fly places with very large batteries. So if that's a concern of yours, we can talk about that later. So we've got Agnes up here in the boreal region, just giving you a kind of an idea of what we're looking at, both in terms of the interface in the upper left. So this is just my Android phone and the Pix4D application. Pix4D is one of these kind of structure from motion softwares where you can actually do flight planning and then also process all of your imagery into actual structural 3D information, which I'll show in a little bit. But what you're seeing here is a flight box, 60 by 60 meter flight box that allows me to fly in a double gridded pattern to see every tree in my in the plot from 4 different angles. So you get a lot of good overlapping imagery. So you're seeing me launch it down here over a bunch of dead black spruce trees. And then if I take those away, you're seeing what I consider my greatest contribution to science thus far is the use of the colorful pool noodle. So you're seeing these crosses are just two different colored pool noodles that we carry around in a golf bag and then lay down, and those become our highly visible GPS targets. So if someone walks around, you can see someone in the upper right corner, and he'll be walking around with a differential GPS and get us those high resolution Earth coordinates to help us more accurately tie down the drone imagery when we get back to the office. So to give you a picture of this particular study area, this is in Bonanza Creek. It's a experimental forest outside of Fairbanks, and just has a range of growing conditions. And so on the left, or excuse me, the bottom middle here, you're seeing one example of a highly productive white spruce and broadleaf mixed forest overlaid by the typical forest inventory analysis plot design. So a single plot comprises 4 subplots that are 120 feet apart from each other, I think. And then on the right, you're seeing a not productive, swampy black spruce stand. And it's these kind of lower productivity areas with kind of less canopy closure and small trees where you really see the value of the super high resolution UAV data, even compared to previously high resolution airborne data. Show that in a second. Right here. So this is the real kind of eye candy here. It's what you can produce by getting all of these overlapping images from UAV. Kind of at least 5 images are generally overlapping at any given point. You throw those into Pix4D or Agisoft PhotoScan or something like that, and you can come out with these beautiful dense point clouds that are also colored. And so you can see a comparison of the resolutions here. On the bottom right, you're seeing that black spruce plot with 2 centimeter resolution canopy height model, where you can really depict every tree pretty nicely and actually get decent descriptions of individual tree structure. And on the left, you've got the 1 meter resolution canopy height model from G-Light, from that Goddard LiDAR hyperspectral thermal. So to be fair, G-Light is pretty darn high resolution and does most of what we need most of the time. But there's sometimes you can go even further. And then don't forget, you also get the color information, so you can actually get the vertical distribution, for example, of color in any given tree, which might provide some useful information about forest health. So we wanted to see, okay, how well can we replicate standard inventory measurements using this individual tree approach based on the drone flights. And so you kind of always start with the basic height measurements. So you see good agreement between the structure from motion heights in these different forest types, particularly down in these very easy to measure black spruce forests versus field measurements. And then when we move into gathering some of the other attributes like biomass and also species classification, I make use of a suite of structural and spectral metrics. So basically gathering data for each individual tree. So what you're seeing here, 3 different species of tree and 3 different and a bunch of different variables, 4 different variables, just as examples of what one might collect that might be useful in a classifier. So one example that I like is the widths at different heights. So just consider the width at 98th percentile height versus the width at median height of, say, a white spruce tree is going to give you, if you take that ratio, it can give you a picture of the conical structure of a spruce tree. And that ratio is going to be very different in a more bulbous broadleaf tree. So just that one kind of simple variable gives you a picture of what the tree looks like and may help with the classification. And of course, you get useful things like just height as well. So that was our goal, was to grab a bunch of these different variables and see what were the most important ones in a classifier to separate out some of the key species: white spruce, birch, aspen, and black spruce. And you're seeing our top 3 variables here chosen through an exhaustive search. So not surprisingly, maximum height in this area was important. Sometimes it's going to be less important in other areas, but here, black spruce and shrub were much smaller. That width at 98th percentile height, again, that kind of indicator of form was important. And then also important was grabbing some of the spectral information. So just the blueness of a tree. You see, something that's very green, like the shrub cover, has very low blueness compared to a black spruce, which had significantly higher blueness. And so this is some value add here that you would not get from LiDAR data, for example. So the ultimate goal here was to take our classification and fuse it with the measurement of these forestry quantities, this tree density, basal area, and above ground biomass. So this is kind of the key value add here, and the key kind of jumping off point for moving forward is how well at each of these plots can you allocate these different quantities. And so what you're seeing here, we just have 5 plots. So these BZ 3 through 7, and you see a comparison of each quantity between field and UAV. So you can see by and large, they match quite well. So, you look BZ6 here, you've got a ton of black spruce tree density as measured by field and UAV. You go over to something like that mixed, that was, you saw the picture of it earlier, that mixed productive environment was BZ7. And you see, well, you get the overall above ground biomass measured pretty well. The species allocation leaves a little bit something to be desired. So I'm overmapping birch compared to what's actually there. So all in all, I think good progress, and something that we're working with Forest Service Pacific Northwest right now to apply more broadly. Okay, so moving from trees into shrubs. So a lot of similar ideas here. And this is now, we're also moving a little bit south from Fairbanks, so interior Alaska, down to the Chugach State Park, which is outside of Anchorage. And the goal here was, it was presented to us by some folks at Forest Service there that, man, there's some really big shrubs in this area that are in fact growing a lot bigger than some of the trees. But tree and shrub in Forest Service land, they are distinguished by their species. And the Forest Service does not tally shrubs. They only tally trees. So they only count, they only add the biomass. And so we think there's a good chance that they are very much undercounting the above ground biomass throughout a lot of Alaska by not accounting for shrubs. So our goal was to start to account for shrub biomass using UAV structure for motion, but then also seeing how well we could do that from G-Lite. So G-Lite also has a high resolution camera on it, 3 centimeter resolution, and also offered potential to map using structure for motion, map shrub biomass, but well beyond the line of sight restrictions that come from using drones. So here's kind of what you're faced with in this environment. So these are mostly willow and alder shrubs, and they're pretty darn big. And think of this in comparison to the size of those scraggly little black spruce trees that you saw in the previous study. Black spruce trees are tallied because they're trees, but they represent a much smaller per tree above ground biomass than some of these shrubs that do not get tallied. So we want to count them, but also it's a real pain in the neck to measure these shrubs because, physically you got to get in with your calipers, and we, had undergrads going into the shrubs and measuring all these different diameters. So it's really something that would be nice to be able to quantify well just from above. Ideally, just like essentially mapping a volume and hoping that biomass can be quantified within that volume. Here's our study area. We're looking at subalpine and upper montane zones. The key kind of differentiation there is subalpine is just going to be shrubs without any overhanging trees. So kind of the easy to measure case. And then upper montane in our definition is going to have a mix of overhanging trees and thus complicate the partitioning of shrub biomass. So here's the nice data page here that shows you the difference between the different ways that one could measure shrub biomass or shrub structure in general. So on the left column is the UAV. So you can see you get a very pretty, realistic depiction of this is a subalpine shrub here. And as you move to the right, you've got the G-Light depiction of this with slightly coarser resolution imagery and fewer images available. Because again, this is a piloted aircraft that doesn't have any side overlap of photos, just front to back overlap. But you can still do pretty well. And then G-Light also has the LiDAR, which is going to have a lot sparser of a point cloud, albeit it's lasers, and so it's going to penetrate deeper into the canopy. And so that's sort of that differential penetration is what you're seeing in the second row. This is a vertical histogram of returns by height, which kind of gives you a picture of canopy structure and density. And you can see that the G-Light and UAV are pretty similar as far as how they're depicting the structure. Overall heights are all the same. And LiDAR is a little different, a little more evenly spread throughout the vertical profile because, again, lasers can penetrate into the canopy, and at least at a fundamental kind of conceptual level, you can't penetrate into the canopy using imagery-based approaches. So how well does all this stuff line up? How well can you measure biomass using either LiDAR or using structure from motion methods? Well, I think the short answer is you can do a decent job using either method. And so you're seeing maps here of one of our study areas, our Arctic Valley study area. And you're seeing biomass from G-Light structure from motion on the top middle and biomass from G-Light LiDAR on the bottom middle. Mostly pretty good agreement. We got a little better precision. So R squared of 0.81 with this structure from motion, perhaps due to denser point clouds or the inclusion of color information. Greenness was important here in the regression model. A little bit lower for LiDAR, but what you can see is in these areas up here that are supposed to be somewhat more free of high biomass shrubs, because if you look over here at the LiDAR height model, you can see this is a subalpine zone with not a ton going on. Structure from motion sometimes can really overmap shrubs based on this kind of uncalibrated color information going a little bit haywire. So there's some benefit still to the stability of LiDAR data, particularly outside of kind of your sampling frame that you've created from your calibration field plots. So just a word of caution. So main lessons from these studies are that, yes, there's definitely value of including this very high density information along with color. It's still important to have a good terrain model existing. Structure from motion in a forested environment is frequently not great at creating a terrain model. So it's good to start with LiDAR and then maybe, do continued analysis and inventory with structure from motion afterward. You need local calibration of the color information. And then we found that, what's nice is you can scale these UAV techniques up to piloted aircraft to cover a lot more area, although computational costs can start to get a little crazy with some of this. Okay, so we're going to rip all of us away from Alaska and back to the city for the next few projects. So this is a quick one that I just think is interesting, well, for a number of reasons, but one, because it presents very, very different challenges to flying a UAV. And so this is with my collaborators at Temple University, and some of their funding is through Department of Transportation to evaluate basically how well different basins, runoff basins, are working along new construction of I-95. So a little different environment than the interior Alaska. And part of what they're doing, for example, is measuring transpiration rates and measuring plant health over time, because it's kind of a cruddy environment. You're getting all this runoff from the highway, so you need plants that can tolerate this well. And something that they were interested in was scaling up their measurements to multiple basin scale. And it seemed like UAV might be a good way to test this out. So, sorry, one thing to point out here is that this is one of the basins that we flew. It's just this strip. And so the big challenge here is this wall. This wall is about 10 meters high, and on the other side of it is I-95. And we could not get permission to fly the drone higher than the wall. So we're basically trying to creep along this wall without running into it. So we're very low. 10 meters is an extremely low flight AGL, above ground elevation, above AGL. Altitude above ground level? Yeah, that's it, I think. Whereas you'd prefer to fly, maybe 70 meters or 50 to 100 meters, something like that. But if you pop that drone above the wall, it could distract the drivers. So anyway, we stayed below the wall, and there's some advantages to that. Like that 10-meter height gives you extremely high resolution if there's no breeze moving the leaves around. And so here's a nice example of an Ortho Mosaic of one of these basins with an 8 to 9 meter AGL and a pixel size of 0.3 centimeters. So that means you can actually look at every little flower. You could count the flowers on all of these plants if for some reason that was your project. But that's not our project. So we wanted to, again, scale up transpiration to the basin scale. And so we're doing this with starting with a simple method here of just making our map on the left, our 3D point cloud of this is Basin A, turning that into a surface model, subtracting out the terrain model made by LiDAR previously. And so basically getting a canopy height model that can be used as a simple way, a starting point to scale transpiration measurements at high resolution over some larger areas. So that's kind of where we're at with this project right now. We'll see what Dr. Josh Kaplan at Temple comes up with in the next few weeks. Hope to submit that paper. Okay, so that was just a little one, kind of a side project for me. And now we're kind of back into the main project over the next few years that we just got funded. And this is where I'm collaborating with Josh Kaplan from Temple and Matt Baker that you guys know well. And so the broad project is urban tree response to heat. And we're looking at it with 3 main research questions, with a focus on transpiration. So I'll come back to the second 2 questions, but the first question is just basically viewing urban tree phenology as the seasonal constraint on transpiration. And so trying to better understand the species and site-specific variability in growing season length. So growing season length being end of season, so when trees lose their leaves that day, minus start of season when trees put on leaves. And so there's a fair amount of evidence that urban areas in general have longer growing seasons than rural areas. But there's more to be said here. For example, if you look at this map that used Landsat data, you're seeing the growing season length difference between urban areas and their neighboring rural areas. So you see some pretty big differences, and it's highly variable across space. Some of it you can already maybe point to some issues here, like the Midwest has huge differences that really may just be looking at crops. So crop phenology is not necessarily an interesting comparison. And then when you get over to our mid-Atlantic area, where some of these, the differences are smaller in magnitude, you still wonder, or I wonder, are the differences, how much of the differences are actually due to phenological plasticity of urban trees in different environments, and how much of it is due to the fact that these satellites are measuring different types of things in the urban area. Like, for example, well-watered turf grass is going to green up earlier in the season than trees. So the more well-watered turf grass you measure, you may be polluting your signal and not actually measuring change in urban trees. So we wanted to look at this at much higher resolution and see what we can see. So was fortunate enough to get a little money from the American University Library to buy a bunch of planet imagery. And the glory of planet here is that it's really kind of the first time that you could marry high temporal resolution, basically almost daily, given good weather, with high spatial resolution also. So either 0.8 meter resolution, which was awesome for SkySat, or 3.7 meter resolution for PlanetScope 4-band. I'll come back to the issues with SkySat in a little bit. Right now, we'll focus on how beautiful it looks. Compared to Landsat imagery, when we zoom in, you can really start to see the phenology of individual trees. So you're seeing tree color in November, lack of leaves, but still seeing grass in March. And then we'll walk through a couple dates here. So we got March 5th, you're basically just seeing grass, quite a bit of shadowing, but no leaves on the trees really. April 1st, some of the leaves start to come out. April 13th, so you got some real pop there of the leaves between April 1st and 13th. So maybe start of season is going to be somewhere in there for a number of species. And then May 7th, you've got basically full leaf out. So we have a lot of those images from 2019 and 2020, and 2018 as well, if you include just the PlanetScope 4-band. So sub-weekly information. And as a starting point, we're looking at 500 different crowns that various grad students have arduously delineated by hand in order to collect 50 different species, 10 different species, 50 replicates of each species across different kind of growing conditions in the city. So in a simple kind of categorical manner, you might be separating out street trees from park trees, for example, but we go a little bit further than that. So a couple examples of the phenological profiles that we've come out with so far at a couple of these individual crowns. You're seeing a red maple in 2019 and 2020. And so you can see you get a really nice profile, given that this is an individual tree, such that you can make an estimate of when start and end of season are. We're using a double logistic fit where you can take some of the parameters to make the fit actually are start of season and end of season, but also you can just take the maximum and minimum of the first derivative of this profile, and that gives you an estimate of start and end of season. So here you're seeing both the PlanetScope 4-band and the SkySat data on top of each other. 2020 for spring, I've removed the SkySat data, and so now is, I guess, a good time to say, like, the SkySat data, while I was super excited about it, a lot of it is highly off-nadir imagery. So you're looking at about, more often than not, it's like 30 degrees off-nadir. And so you get some really challenging BRDF effects. So effects that change the reflectance a lot in ways that aren't related to actual change on the tree. So it's even after applying some corrections, it's still a very noisy data set compared to PlanetScope 4-band, which it's basically always looking down from directly overhead, plus or minus like 4 degrees. So that has made a huge difference. And so I've accepted that we're at 3.7 meter resolution instead of 0.8 meter resolution to gain that consistency of view angle. So happy to, I won't go more into that, but I'm happy to talk about that more later on if that's of interest. So back to our profile here. I think something that's interesting to note that may merit further study is the difference in the slope between the 2019 and 2020 green up. And I didn't notice this initially, but then I read an article in from the US, what is it, US Phenological Network, I think, basically pointing out that, hey, in 2020, it started out really warm. So February and particularly March was quite warm. And so the early start of season, which may be depicted by this inflection point here, this change in curvature, that started quite early. But then later on, we had this kind of flip in weather where late April and May were actually quite a bit cooler than normal. And so it may have had the effect of actually extending out this growing season. So yes, it started earlier, but it actually may have ended later than in 2019. So so far, I'm seeing this in a lot of the data that we're looking at. So just one more thing that we can study from these profiles. So, you know, same general idea from an American elm. And so multiply this by 500 and you've got our basic working data set. So those profiles look pretty good, but we need to get some validation, some on the ground validation here. And so this is where the real work comes in. So I partnered with Casey Trees, which is an urban forestry nonprofit in DC. I used to work for them a while back, and they got a list of, they got 70 people who were interested in hosting phenocams at their house, which was great. And so we were able to buy like 20 of these Brino time-lapse cameras. They're basically used for like security site, security cameras at construction sites, but they also can be used for time-lapse videos of phenology. And so we, at each of these volunteers' houses, we either stuck it on a suction cup, looking out at some trees. So this is the view from my new office. Pretty excited. Someday we'll go back there. And this on the right is one of our houses on Trinidad Street Northeast, one of our volunteers that has a nice view. You know, we could probably get like 6 or 7 validation trees, which means 6 or 7 trees where we can line up what we're seeing from this weird angle with what we're seeing from the satellite data. More challenging than you might think to figure out which tree is which. So we've got, I think, like 15 or 17 of these cameras around town right now, just doing their monitoring. And so we've got some validation data already made and some is yet to come. So here's what you can see. This is First Street Northeast through someone's front window on their living room. You can obviously see a change in greenness between March and June of 2020. End of season from 2019. This is from my high school buddy's roof in Capitol Hill. You can see some nice flaming red maples, and then I think some wind comes in and pulls those leaves off pretty quick. So here's another good grad student task here is how do you get this image information into actual data? Well, each tree that you can match up with satellite, with some of this CubeSat data, becomes a region of interest. And from there, you can extract kind of the typical method is you extract green chromatic coordinate, which is basically just the greenness normalized by green plus red plus blue information. And you watch how that changes over time. And so on the right, you're seeing a spline fit for what is this, ROI1. So you're seeing it's a maple tree that turns red. So you see the decline in greenness, a lot of that being driven by the increase in redness So these maple trees in particular have these big troughs where peak of redness is actually the lowest point of greenness. And then you have a recovery afterward back to kind of this baseline, which is really just means that you're seeing this grayness, kind of a gray, urban scene with branches and buildings in it. So it actually becomes a bit of a conceptual challenge, and I'm open to discussion on this one for what is end of season for these type of trees. It seems it's different than measuring using NDVI from above, and I'm not entirely sure the best way to do it. That said, most of my trees are not flaming red maples, and so this problem is not quite as pronounced throughout much of the study area. So that's kind of where we're at right now. Is I'm kind of putting the finishing touches on this early validation at like 60 different rounds across all these different cameras, and my grad student finally gets to stop drawing ROIs and start actually looking at these species level and site level differences within a year and across years for 3 years. But then what's next? So this is where I come back to the other two questions that I didn't get around to mentioning with this urban tree response to heat. So we've got the phenology, which is the seasonal bounds, but what we also are interested in is the subdiurnal bounds and some other changes in response to heat. And so let me talk about the first one, the heat response first. So this is collecting urban heat island anomaly temperatures, because part of our project was saying how much is end of season impacted by cumulative heat load, for lack of a better phrase at this point, at a given place. So kind of the spatial anomalies of air temperature, is that going to always make growing season length longer? Or is sometimes, if the heat load is so high and the conditions are so unappealing, that could mean a lack of available soil moisture, is leaf abscission actually going to be earlier than you'd expect at these high heat areas? And so we have multiple ways to get at this question, but my COVID-friendly field work for this summer, because I couldn't go to Alaska, was actually to outfit my 2003 mountain bike with an air temperature monitor. So you can see it's on this mast. It's measuring air temperature every 5 seconds with pretty quick response time. And I've been doing these rides around DC. So there's 3 routes, each of which are about 22 miles, and they traverse a gradient of canopy conditions and impervious surface conditions. They try to go past all the phenocams for what that's worth. They try to kind of do it all. And these are captured at probably the two least appealing times of day to be on a bicycle, which would be the hottest time of the day, so roughly like 3 to 5 p.m., and then the coolest part of the day, which is 3 a.m. to 5 a.m., 4 a.m. to 6 a.m., more or less. So the latter one there is a little more for another master student who's just doing some local climate zone mapping in DC, since that's kind of when their boundary layer stability is at its highest, and it's the best time to measure urban heat island effects. The afternoon is a little more of interest to what is the plant response to these different temperatures. So we are currently analyzing those data. In the future, we will go to this high resolution thermal mapping to see, okay, how does transpiration change by species and over time? What is kind of the subdiurnal changes in transpiration, and how well can we measure this using drone imagery? So we'll reintroduce Mo, the radiometric thermal drone from before. He'll finally get to come out and fly over perhaps UMBC campus, probably, fly over a bunch of trees that are also outfitted with sap flux measurements as valid, and then extend that transpiration model based on the difference between leaf temperature and air temperature to a much wider array of trees. Ultimately leading us to some other questions about whether trees under hotter conditions are starting to actually optimize for thermal regulation rather than strictly optimizing for carbon gain. And in this case, we might be seeing a decoupling of transpiration and photosynthetic activity, as has been viewed in some laboratory conditions in certain species over the last 5-10 years. So that's the most future portion of what we're on, but should be sometime in the next couple years. So that's all that I have for you for right now. I'm happy to take any questions or take any comments.
So I will just encourage people to put questions into the chat, and then Michelle is going to call on people. If we don't see questions showing up in the chat, then we will just ask people to unmute themselves. Always like to encourage the graduate students to speak first, because the faculty will jump into the breach if you don't.
I guess I had a question.
Actually, there is a question in the chat.
Oh, there is one?
Yeah.
Okay, I guess I'm... Okay, do you want to...
Michelle, why don't you go ahead and read the question,
Okay.
or you can ask the person ask the question on mute and ask it themselves.
Okay, I'll just ask it since I'm not muted. Okay, so what was the inspiration for measuring using the bicycle?
Well, we did. I mean, I guess I should start with the science goal. The science goal was to measure. Well, it was two main ones. It was, again, I had a master student who's interested in urban heat island, and was seeing about making a better map of local climate zones. So how air temperature, particularly under calm evening conditions, how temperatures vary based on urban structure. So, you know, temperatures are frequently going to be higher at night where there's tall buildings and lots of impervious surface, and they're going to be lower at night where there's fewer buildings because there's less long wave trapping in those areas. And so she was trying to improve on the mapping of those zones, which can play into kind of zoning decisions if you want to talk operationally. And so doing these bike routes at night allows you to kind of do, in simple terms, just like an analysis of variance to see whether the zones that have been created based on kind of urban biophysical structure actually line up with the variance of air temperature. You know, in a perfect world, you would have very low within zone variability in temperature, and you'd have very high, relatively high among zone variability in temperature. And that does bear out at night, more or less. So that's the nighttime goal. And so the daytime goal was repeat measurements of urban heat at a finer spatial scale. So there's a paper, the direct inspiration is a paper by Carly Zeiter, who is at Concordia University now in Montreal. And she was looking in Madison, Wisconsin at the time at the scale of the effects of canopy and tree canopy and impervious surface on temperature. So does the amount of canopy matter most at 10-meter scale, 10-meter buffer, say, or does it matter most at 90-meter buffer? And so, kind of thought it'd be interesting to see how this played out in a hotter mid-Atlantic environment, larger city, and B, wanted to tie into the phenology. So now why a bike in particular? That's more that I like riding around. I needed an activity in the summer to get me out of the house so I didn't go crazy. And it was a good actual use of money because the original plan for measuring urban heat island was to buy about 20 hobo air sensors and distribute them. And so those are like $200 a piece times 20 is like $4,000. And you get really good temporal resolution on that, continuous, but they're fixed location. And so it kind of turned out that I think the relative merits of lower temporal resolution, kind of lower repeat, fewer repeats, was outweighed by the benefits of covering an arbitrary amount of ground. So I certainly sampled in many more locations using the bike than we would have using fixed sensors. If you're really going to go to town, like Madison, Wisconsin, they outfitted the city, a much smaller city with, I think, like 150 hobo sensors. And so they got the best of both worlds. Our money and our priorities did not allow for that. So that's why the bike happened.
Okay, we have another question from Kirk. It says, has any consideration been given to placing log tag sensors to record temperatures continuously over time?
What was the
record temperatures? Has any
log tag?
Sorry, log tag. I can repeat. Has any consideration been given to placing log tag sensors to record temperatures continuously over time?
I don't think I know what a log tag sensor is.
Well, there's a link in the chat, so if anybody has any interest, you can click.
Maybe Kirk.
So yeah, I guess
since he knows what.
Yeah,
different. If it's just a fixed sensor that measures temperature, then I think that might be the same reason for not doing the hobos. But if it's something different, then I would be open to talking about it. But I don't at the moment. I do not know what it is.
Kirk, you want to say a word about it since you asked the question? I don't know if you're trying to talk, but you must be muted.
Doesn't look like he's muted.
Okay.
Don't hear anything though.
Well, since he asked that question, I'll just ask. I mean, we have used iButtons for things in the past, which are pretty inexpensive. I don't know whether they're just not good enough in terms of quality or what. But.
Yeah, no, I think it just isn't that temporal resolution isn't the main priority of work right now, and so it was more useful to just get a general sense of the anomalies. We basically like the repeating repeat in a given area at some level only mattered to just see if the temperature anomaly was stable or not. Like, is an area that was hot on bike ride number 1 in July, is that same area still hot on bike ride number 2 in July and number 3 in August? So it gives you a little sense of the variability and some sense of whether you can just kind of develop your own cumulative heat load just based on temperature modified by the anomaly over time, or whether you actually do need to continually remeasure. So Dr. Vivek Shandes and his collaborators did a 2018, I think, single day similar type of study in DC, Richmond, and Baltimore. And they used cars for that because they went like all in, and they covered a lot of ground. Over one day, they did hour-long drives in the early morning, before sunrise, heat of the afternoon, and then early evening, I think. So, one little thing we wanted to see is how much does, their map of temperature change over time, or, is that one-time measurement sufficient? So we're kind of looking at that right now, and I think it does change some over time. There's definitely some time effects, and there's just a lot of difficulties in making these kind of measurements, frankly.
Other questions?
All right, Matt Fagan has a question. Matt Fagan, would you like to unmute to ask? Okay. Could you speak to the effects on warming on conifers versus deciduous species?
Not yet. No, I don't know. I mean, because in our area, I pay very little attention to conifers in the urban zone because they're not very prominent. So, you're not going to see a phenological effect. We're not going to be measuring them from the UAV because again, there aren't very many of them, and I think it'd be challenging. Also, moving into needle leaf work has some technical difficulties. There's some more papers that have been coming out recently on like photosynthetic phenology, or different measures of kind of plant productivity that are geared towards conifers. So more in like the northern realms, basically. Like John Gammon does some work on that, so that'd be a good place to look. But I only dabbled in that a little bit myself.
Matt Baker, would you like to ask next?
Sure. Hi, Mike. I'm thinking about the shrub work you were doing, and where you're comparing LiDAR and SFM from the G-Light sensor, but also from a drone. And I'm wondering, when you were sort of analyzing the histograms of the point clouds, whether you were able to separate the edge of the shrub and its points from internal structure. So sometimes when I look at those histograms, especially from structure from motion, I wonder whether the lower height points that are perceived by structure from motion are really the edge structure of the vegetation and not internal to the shrub.
Yeah.
And I was wondering if you were able to separate those at all.
Yeah. So certainly that was my first, like when I look at a picture like that, I'm like, oh, well, that vertical distribution is based on the fact that we're seeing the edge. And so went back in and made sure that some of our plots, so this one, for example, has no edge in it. And we were able to kind of look, you are seeing somewhat inside of the actual crown. And so part of my thought there is just, you can't penetrate through anything using imagery-based approaches, but there is a scale consideration of, you can certainly see smaller gaps. You can see a lot smaller gaps when you're measuring at 1.5 centimeter resolution than you can with a lot of the previous studies that have been done comparing LiDAR with structure from motion that have used an order of magnitude, at least coarser imagery, something like 0.2 to 0.3 meter imagery was what they were using. So it kind of stands to reason. We make the argument that due to that scale dependence, or that you should be able to see deeper into canopy into smaller holes, even though there's no actual penetration. So I think it's an area for kind of more, we sort of, we observed this, think, and make some general arguments as to why it might be true. I think there's certainly more room for deeper analysis of that.
Cool, thanks. We observed something similar on our knoll here on campus. And It's always been something that I've wondered about, whether we're actually perceiving features versus the absence of features. And like wherever the shadow runs out is where there's a point measured and structure from motion. Yeah,
I don't know. I've spent a lot of time staring at these things to convince myself that what I was seeing was real and not, I wasn't cheating in some way. I always assume that I'm cheating when something works out well. Unclear.
Okay.
So we're at 1 o'clock, and so I'm sure some people have to go. I think there's one more question. Maybe Jason wants to ask that. Other people need to leave. The last thing I'll say before we take that last question and stop the recording is that some folks are going to join in a separate virtual lunch session. So Michelle arranged that, and if you have the link for that, we will close this session, stop the recording, and then immediately convene in that session. If people need to go get a sandwich or something, then you can just kind of wander in. So if anybody does not have the link that wants it, you should let us know right now so that we can get it to you. But go ahead, Jason, why don't you ask your question, and then we'll bring this to a close.
Oh yeah, sure. No, I was just curious if you had any preferences on photogrammetry software you might like using. I've had the pleasure of using quite a few over the summer. So I just, what kinds of different purposes you like, for what different software you might prefer for different purposes, I guess. Muted. You muted, Mike.
Oh, muted. How'd I get muted?
You're good now, Mike.
Okay, I don't even know how to mute myself anymore. Sorry. Okay, so yeah, one trick pony. Really, have only used. I mean, I've used Agisoft PhotoScan a little bit a few years ago, and you know, the results were fine, but the workflow, I found the Pix4D workflow to be very nice, and I feel like I'm not trying to go super deep into the photogrammetric kind of underpinnings. I hope to be a little more of an applied user. And so to the extent that I can have the product not be a complete black box, but also be relatively easy to use and computationally helpful, then I'm happy with it. So by computationally helpful, I mean, I like Pix4D's cloud processing platform that I just upload these rather large point clouds and do my initial processing there, bring the results back down and re-optimize based on our geographic or our GPS data, and then send it all back up to the cloud to do the point cloud densification and the making of well, that's really where I stop. Then I make my own canopy height models and whatnot. And so far for the multispectral work, Pix4D has been fine too, as far as creating outputs like, you know, basic vegetation indices like NDVI, red edge NDVI, or just the raw bands based on calibrated reflectance. I thought it's worked reasonably well so far. Thermal have not even really tried yet. So the thermal, I'm just working right now to do the proper corrections to get to raw temp, to get to a proper temperature estimate of a surface. And so I'm kind of doing that before I get into any use of Pix4D or other software. So that's where, you know, if you're coming to lunch or have any suggestions of things that you'd like, I'd be happy to hear them, because I'm a little more of an end user, I suppose, as far as the software goes.
Yeah, sure. Thank you. Appreciate it.
Okay, I think we are at a stopping point. Michelle, you want to wrap up, and then I'll stop the recording, and then anybody who's coming to lunch, we have that separate link, which you should already have if you're coming.
Sure. Okay. Thanks, everybody, for coming. And we're going to be having a lunch discussion for during the next hour. And I sent out an email with a link. And so if you're missing the link, feel free to email me and I'll let you in. So, bye, everybody.
Okay, thanks, Mike. Thanks, everybody, for attending. And those of us who are going to lunch, will reconvene momentarily.
Thank you. Thank you all.